Good morning, students. Welcome to our daily discussion for this morning. And this is my final report in number theory, book of David Borton. My topic for today is all about sums of two squares, chapter 12.2, pages 262 to 271. So my name, by the way, I am Raymond Belchar, a second year student in GHCSC Dumiang campus. So let's explore the sums of two squares. So our learning objectives for this morning. At the end of the lesson, the students will able to understand the concept of sums of two squares and solve the sums of two squares. Let's begin with a simple question. What is the smallest value n such that every positive integer can be written as the sum of not more than n squares? Basing on these numbers or these few positive integers in your screen. Yes, Arshel Kulot. Thank you. Who else? Who have the brightest idea with regards to this question? Yes, Miss Octaviano. That will help. Okay. So since 4 squares are needed in the representation of 7, n is greater than or equal to 4. So kung akong bisayon, kung inyo makita di ara sa board ninyo, sa inyong screen, ang number di ara 1 is to 7. 1 to 7. So, paabot og 7, na imong upat na kabuk na ang number di ara. So therefore, if we are going to analyze the numbers, let's start with number 1. We have there 1 equals 1 square and 1 square is equal to 1. So 1 equals 1. The same with 2. 2 equals 1 square plus 1 square. 1 square plus 1 square is 1 plus 1. So we have 2. And so on and so forth. It is just the same with number 7. But when we are going to number 7, you need some numbers nga kailangan nga mapuno nga may mo siyang 7. Okay? So, our first lemma for our topic in this morning is all about m and n are each of the sum of two squares, then so is their product mn. If m equals a squared plus b squared and n equals c squared plus d squared for integers a, b, c, d, then mn equals a squared plus b squared times c squared plus d squared equals to a squared plus b d squared plus the square of ad minus bc. It is clear that not every prime can be written as the sum of two squares. For instance, 3 equals a squared plus b squared has no solution for integral a and b. More generally, one can prove that in theorem 12-1, no prime p of the form 4k plus 3 is a sum of two squares. Proof. Modulo 4, we have a is congruent to 0, 1, 2, or 3 for any integer a, hence a squared is congruent to 0 or 1 modulo 4. It follows that for arbitrary integers a and b, a squared plus b squared is congruent to 0, 1, or 2 modulo 4. Since p is congruent to 3 modulo 4, the equation will become impossible because there will be no integers that would result 3 into a squared plus b squared. On the other hand, any prime which is congruent to 1 modulo 4 is expressible as the sum of two squared integers. The proof in the form we shall give it employs a theorem on congruences. Theorem 12-2 Fermat, an odd prime p is expressible as a sum of two squares if and only if p is congruent to 1 modulo 4. Proof. While the only if part is covered by theorem 12-1, let us give a different proof here. Suppose that P can be written as the sum of two squares, say P equals A square plus B square, because P is a prime. We have P does not divide A and P does not divide B. If P divides A, then P divides B square. And so P divides B, leading to the contradiction that P square divides P. Thus, by the theory of linear congruences, there exists an integer C for which BC is congruent to 1 modulo P. Modulo P, the relation of square AC plus the square BC is equals to the PC square, becomes the square AC congruent to -1 modulo P, making that -1 is a quadratic residue of P. Corollary. Any prime P of the form 4k plus 1 can be represented uniquely aside from the order of the summands as a sum of two squares. Proof. To establish the uniqueness assertion, suppose that P is equals to A square plus B square equals C square plus D square, where A, B, C, D are all positive integers, then A squared D squared minus B squared C squared equals P times D squared minus B squared is congruent to 0 modulo P. Whence AD is congruent to BC modulo P, or AD is congruent to negative BC modulo P. Since A, B, C are all less than square root of P, these relations imply that AD minus BC equals to 0 or AD plus BC equals to P. So if the second equality holds, then we would have AC equals BD for P square equals the product of A square plus B square and C square plus D square equals the square of AD plus BC plus the square of AC minus BD equals P square plus the square of AC minus BD. And so AC minus BD equals 0. It follows that either AD equals BC or AC equals BD. Suppose for instance that AD equals BC, then A divides BC. With GCD, AB equals 1, which forces A divides C. Let us say C equals key A. The condition AD equals BC equals B times key A then reduces to D equals BK. But P equals C square plus D square equals the product of K square and A square plus B square, implies that K equals 1. In this case, we get A equals C and B equals D. By a similar argument, the condition AC equals BD leads to A equals D and B equals C. What is important is that in either event, A square plus B square equals C square plus D square, justifying the stated conclusion. So, remark. Some authors would claim that any prime P is congruent to 1 modulo 4 can be written as a sum of squares in 8 ways. For with P equals 13, we have, so 13 equals 2 square plus 3 cube. No, it's not 3 cube. That is 3 square. Okay? That is 3 square. If you're going to simplify 2 square and 3 square, that would be 4 and that would be 9. So 2 plus 9, 4 plus 9, and we have 13. That is our first way on how we solve our P. And then we have then 2 square plus negative 3 square. And or it can be negative 2 square plus 3 square. It can be negative 2 square plus negative 3 square. It can be 3 square plus 2 square. It can be 3 square plus negative 2 square. Or it can be negative 3 square plus 2 square. Or it can be negative 3 square plus negative 2 square. We have shown that every prime p such that p is congruent to 1 modulo 4 is expressible as the sum of two squares, but other integers also enjoy this property. For instance, for example, 10 equals 1 square plus 3 square. If we're going to simplify 1 square and 3 square, we have the result 1 plus 9, and then that would be equal to 10. So 10 equals 10. And for our theorem 12 to 3, let the positive integer n be written as n equals big letter N square m, where m is a square free. So be represented as the sum of two squares if and only if m contains no prime factor of the form 4k plus 3. Proof: to start, suppose that m has no prime factor of the form 4k plus 3. If m equals 1, then n equals big letter N square plus 0 square, and we are through. In the case in which m is greater than 1, let m equals p sub 1, p sub 2, ellipsis p sub r be the factorization of m into a product of distinct primes. Each of these primes, p sub I, being equal to 2 or of the form 4k plus 1, can be written as the sum of two squares. Now the identity, the product of a square plus b square and c square plus d square is equal to square of ac plus bd plus the square of ad minus bc. Thus, there exist integers x and y satisfying m equals a square plus y square. We end up with n equals n square m. And then we have n square plus, we're gonna substitute the x square plus y square to m right there if you are following my red light. So we have then in x square plus the square of ny, a sum of two squares. For example, for 12.1, the integer 459 cannot be written as the sum of two squares since 459 is equals to 3 cubed times 17. Reminder, it is the sum of two squares. We will not include cube here. So with the prime 3 occurring to an odd exponent, on the other hand, 153 is equals to 3 square times 17 admits the representation of 153 equals 3 square times 4 square plus 1 square equals 12 square plus 3 square. There exist certain positive integers, obviously not primes, of the form 4k plus 1, which can be represented in more than one way as the sum of two squares. The smallest is, for example, number 425 equals 4 square plus 3 square, and then it can be 5 square plus 0 square. So if you're going to simplify 4 square and 3 square, we have the result of 16 plus 9. And so with 5 square plus 0 square. So if you're going to simplify 5 square and 0 square, that would be 25 plus 0. So if A is congruent B modulo 2, then the relation is AB equals to square of A plus B all over 2 minus the square of A minus B over 2. Allows us to manufacture a variety of such examples. Take n equals 153 as an illustration. So we have there the example. So 153 equals 17 times 9. Okay? We're going to factor. And then we have the result 17. The square of 17 plus 9 over 2 minus the square of 17 minus 9 over 2. And then we have the result of 13 square minus 4 square. If you're going to simplify 13 square minus 4 square, and then you will have the result of 153. This and 153 equals another factor of 153 is 51 times 3. So we have the square 51 plus 3 over 2 minus the square of 51 minus 3 over 2 equals 27 square minus 24 square. So that 13 square minus 4 square equals 27 square minus 24 square. Why? If you are going to simplify 13 square minus 4 square and 27 square minus 24 square, you will have the same result of 153. So therefore, 153 is equals to 153. So theorem 12 to 4. A positive integer n can be represented as the difference of two squares if and only if n is not of the form 4k plus 2. Proof. Since a squared is congruent to 0 or 1 modulo 4 for all integers a, it follows that a square minus b square is congruent to 0, 1, or 3 modulo 4. Turning affairs around, suppose that the integer n is not of the form 4k plus 2, that is to say, n is congruent to 0, 1, or 3 modulo 4. If n is congruent to 1 or 3 modulo 4, then n plus 1 and n minus 1 are both even integers. Hence, n can be written as n equals the square of n plus 1 over 2 minus the square of n minus 1 over 2. That is a difference of squares. If n is congruent to 0 modulo 4, then we have n equals the square of n over 4 plus 1 minus the square of n over 4 minus 1. Corollary. So this would be our last corollary for our topic for this morning. So an odd prime is the difference of two successive squares. For example, 11. 6 squared minus b squared. If you're going to simplify 6 squared minus b squared, you will have 36 minus 25. So 36 minus 25, and then you will have 11. The same as 17. 9 square minus 8 square. Simplify the squares of the number. You will have 81 minus 64, and then you will have 17. And same with 29. So 15 square minus 14 square, and then you will have 29. So, students, thank you for listening for our discussion for this morning. I hope you understand the concept of the sums of two squares. But before that, you are going to screenshot the quiz for this morning. We have there test 1 and test 2. So it's just simple. The test 1 is all about find the sums of two squares. That would be 5 points each. And for the test 2, find the successive squares. 5 points each also. So take a screenshot. And what time is it? It's OB time. So it's 1:50 in the afternoon. You're going to pass your quiz 2:30 in this afternoon. So screenshot the quiz. So I hope that you understand our discussion for this afternoon. So good luck for the quiz, and thank you also everyone.